Okay, this is discussion 3. We're going to talk about limiting reactants. We're going to review percent composition and empirical molecular formula, and we're going to show how we can use what we've learned in this unit to connect those two. Alright, so when we talk about limiting reactants, it's helpful to think about something really concrete, like making turkey sandwiches. So let's say that I had 10 pieces of bread, but only 4 portions of turkey. How many sandwiches could we make? Okay, well, with that amount of bread, we could make 5 sandwiches, but we're going to run out of turkey at 4 sandwiches. So that means that we can only make 4, right? Because the turkey's going to run out, and then we'll have 2 pieces of bread left over. So the limiting reactant is what runs out first in a chemical reaction, and it determines the amount of product that can be made. So in the above example, the turkey was the limiting reactant because it limited us to 4 sandwiches. The excess reactant is the reactant that we have more than enough of, and so we're going to have leftovers at the end. So in this case, the bread would be the excess reactant because we had 2 pieces of bread left over. Now, what we're going to do when we solve these problems is we're going to figure out how much product each reactant could yield and compare the results. Whichever makes less product will be the limiting reactant, and the amount of product that the limiting reactant makes will be the theoretical yield. Okay, so let's look at a chemical example. So this says that sodium hydroxide reacts with carbon dioxide by the reaction below. Okay, so let's say we have 1.85 moles of sodium hydroxide and 1 mole of CO2 reacting. Now, before you did any math, you might say, oh, well, I have less CO2, so that must be my limiting reactant. But that's not quite true, because if you look at the balanced equation, you'll see that we need 2 moles of sodium hydroxide for every 1 mole of CO2. So a way to avoid this error is to set up 2-dimensional analysis problems. So to figure out the limiting reactant, we can convert both reactants to one of the products. Now, there's 2 products in this equation, so it's hard to know which one you should convert to. But if you look at the second question, it says how many moles of sodium carbonate can be produced. So if we just convert to moles of sodium carbonate, we can save ourselves another step later. Alright, so with 1.85 moles of sodium hydroxide, I can make 0.925 moles of sodium carbonate because the ratio is 2 moles of sodium hydroxide to 1 mole of sodium carbonate. But with my CO2, I can make 1 mole because the ratio is 1 to 1. So we see that just because I had less CO2 doesn't mean it would make less product. In fact, it makes more. So my limiting reactant is sodium hydroxide because it makes less product. So how many moles of sodium carbonate can be produced? Well, to find that answer, we're just going to look at the question above, and we're going to take the lower of the 2 results. So 0.925. Now, another common question is how many moles of excess reactant remain? So in this case, I have to say, okay, first, what's my excess reactant? CO2. Now, before I know how much remains, I have to know how much I used. So one way to do that is to say, okay, I need to find out how much CO2 I needed to completely react all the sodium hydroxide. And when I do that math, I find that I needed 0.925 moles. Since I had 1 mole to start with, I can subtract 0.925 and get that 0.075 moles of CO2 remain. Okay, now let's look at a slightly more complex problem. It's not necessarily harder, but in this case we're using grams instead of moles, so the conversions will be a little bit longer. Alright, so we have 40 grams of benzene reacting with 65 grams of bromine. Okay, now this doesn't actually use the words limiting reactant in the question, but we know that that's what we have to do because we have 2 givens. Right, we're given amounts of both reactant. Normally, we would just had 1 given and 1 thing we were solving for, but here we have 2 given, so that should be our clue right away that it's really a limiting reactant problem. So if we want to know how many grams of bromobenzene are formed, we need to convert both of those to grams of bromobenzene and see which yields less. So these are gram-to-gram problems, so they'll take a little bit more doing. But when I convert grams of benzene to grams of bromobenzene, I get 80.4 grams. When I convert grams of bromine to grams of bromobenzene, I get 63.9 grams. So pause for a second and see if you can identify the limiting reactant and the theoretical yield of bromobenzene. Okay, the limiting reactant is bromine because it makes less bromobenzene. And the theoretical yield is 63.9 grams of bromobenzene. Okay? It really bothers people to have done 2 problems and then only use 1 in their results, but try to accept that because that's how this works. All right, so since we just figured out the theoretical yield, you might remember in Lab 6.2 we calculated a percent yield. So percent yield is the actual or experimental divided by the theoretical value times 100. So this says if the actual yield of bromobenzene was 52.4 grams, what is the percent yield? All right, so we take 52.4 divided by 63.9, multiplied by 100, and we get 82.1%. Okay, and you can, if you have the percent yield, you could solve for a proposed experimental value. Lots of different ways that you can use this. Okay, let's quickly review percent composition from Unit 4, Topic 3. Percent composition just is percent by mass, so it tells how much mass each element contributes to the total mass of the compound. So if we wanted to find the percent composition of copper in copper 2 chloride, we would take the mass of one copper atom, because there's only one copper atom in the compound, divided by the total mass of all atoms in the compound, so 1 copper and 2 chlorines, and multiply by 100, and we get 47.27% copper. Now, the reason we're reviewing this is that based on what we've learned about mole conversions, we can now use percent composition to find the empirical formula. So let's review that. Empirical formula is the simplest whole number ratio of elements in a compound. So for example, if we had benzene, C6H6, its empirical formula would be CH. Now to find this, first we have to find the number of moles of each element. And then we need to relate them, find a whole number ratio between moles of the element. So the easiest way to do this is to identify the smallest number of moles and divide all the moles by that number to get a whole number ratio. Okay? If it's really close to a whole number, you can round. If you get something like 1.5, then multiply all of your numbers by 2 to get a whole number ratio. So the easiest way to understand this is to look at a bunch of examples. So let's do that. Okay, first, it says find the empirical formula of a compound containing 10.52 grams of nickel, 4.38 grams of carbon, and 5.1 grams of nitrogen. All right, so let's look back at our steps. First, we have to find the number of moles of each element. Okay, so converting grams of nickel to moles, grams of carbon to moles, and grams of nitrogen to moles. Okay? Now, I know I can't write my formula as nickel subscript 0.179, carbon subscript 0.365, and nitrogen subscript 0.364. I just can't do that. That's not how we write formulas, because you can't have 0.179 of a nickel atom. So I need a whole number ratio. So I'm going to identify the smallest number of moles, which in this case is 0.179. Then I'll divide each number of moles by that. So I'll get 1 nickel, 2 carbon, and 2 nitrogen. Okay? So then my empirical formula is NiC2N2. Now, in this other example, this is one that often trips people up. You're actually given moles here of nitrogen and hydrogen. So you don't have to do any kind of dimensional analysis conversion. All you have to do here is divide by the smallest number of moles, and you get 1 nitrogen and 2 hydrogen. So I show you this not because it's especially difficult, but just to show you that sometimes you'd be given moles and it's quite a straightforward problem. Okay, now, when we look at empirical formulas from percent composition, we have to make an important assumption. So if we were trying to find the empirical formula of a compound that's 41% carbon, 5% hydrogen, and 54% oxygen, initially it seems kind of hard because how are we going to get to moles from that? But if we remember that this is percent by mass, it becomes a lot easier. Let's say I had 100 grams of this random substance. Okay? Since this is percent by mass, if I had 100 grams of the substance, 41 grams would be carbon, 5 grams would be hydrogen, and 54 grams would be oxygen. Okay? So, I'm going to start by assuming 100 grams and then taking those percentages to be the masses in grams. Okay? So from here, I would pause and see if you can find the empirical formula using the same process we used 2 slides ago. Okay, so converting to moles, dividing by the smallest number, and figuring out the ratio. Okay, so first we convert to moles, identify the smallest number, and divide by that. Smallest number is 3.38, so we get approximately 1 carbon, 1.5 hydrogen, and 1 oxygen. But we can't have a subscript of 1.5, so then we have to multiply all of those by 2. So then we get 2 carbons, 3 hydrogens, and 2 oxygens. So our empirical formula is C2H3O2. Now, You might remember that the molecular formula is the actual formula of a compound as it exists in nature. So this gives you a series of compounds that all have the same empirical formula. If you look carefully at their masses, you'll notice a pattern. So first I have CH4, and it has an approximate mass of 16 grams per mole. When I multiply both of the subscripts by 2, so it's still going to reduce to the same thing, note that I've also multiplied my mass by 2. When I multiply both of the subscripts by 3, I've also multiplied the mass by 3. So let's say that I had a compound that I knew had empirical formula CH4 and the molar mass was 80. Well, I could just take 80 by 16 and I'd get 5. And that's how I'd know I have to multiply all my subscripts by 5. So if you have the empirical formula and the molar mass of the compound, you can find the molecular formula. First, you have to take the molar mass of the compound and divide by the molar mass of the empirical formula, and that'll give you a whole number. Then you'll multiply the subscripts of the empirical formula by that number to get the molecular. So, here's an example. The empirical formula of the anti-cancer drug called altretamine is C3H6N2, and its molar mass is 210 grams per mole. Alright, so, first, let's find the molar mass of the empirical formula. So it's about 70 grams per mole. Now, we have to figure out what we need to multiply those subscripts by. So, if we take 210 and divide by 70, we'll get that multiplier, and it's 3. So to get the molecular formula, we have to multiply all of the subscripts in the empirical formula by 3. And so the molecular formula is C9H18N6. Okay, for this last problem, you're going to combine two approaches. So first, you're going to use percentages to find the empirical formula. Next, you'll use the molar mass of the compound in the empirical formula to get the molecular formula. So pause and try to do this yourself, and then we'll go over it. Okay, first, remember we're going to assume 100 grams of the substance and convert to moles. So we get 6.24 moles of nitrogen and 12.5 moles of hydrogen. And we're going to divide by the smallest number, which is 6.24. So we get approximately 1 nitrogen and 2 hydrogen. So that means that our empirical formula is NH2. Its mass is 16.03 grams per mole. So I have to take the molecular formula mass and divide it by the empirical formula mass. And when I do, I get roughly 2. So that means that I have to multiply my subscripts by 2. And if you wanted to, you could double check and make sure that this mass works out, right? I could calculate the mass of N2H4 and make sure it's about 32.05, okay? If it's a little off, that's okay. It's probably because of rounding. But you can check yourself at the end on these. Okay, so as soon as you can, try to do the practice because there's a lot in this topic, even though this was a pretty short video, and the only way to get better at this is practice. There's a lot of steps to keep track of. And come see me for help. Okay, good luck.